At this very moment, you're soaring through the universe at more than 560,000 miles per hour, riding a colossal cosmic carousel so immense that even light would need 100,000 years to travel from one side to the other. This swirling sea of 400 billion suns is our home. We call it the Milky Way. Yet we've never gazed upon it from the outside. We've never truly seen the grand scale of the galaxy that shelters us. But tonight, that changes. Together, we'll venture to the edge of our celestial realm and uncover that what we know about size, distance, and our position in the cosmos is only the beginning. If you're ready for this interstellar journey, tap that like button and join the adventure. Buckle up. Our voyage begins now. Astronauts often talk about the first time they see our planet from orbit. They lean close to those small spacecraft windows, eager to spot something familiar. A coastline, a mountain range, maybe even their city. But what they find instead is humbling. The places that once felt immense, sprawling cities, winding roads, and massive lakes, reduced to faint specks and shimmering threads of light. The continents stretch out like paintings beneath them, and as their eyes trace the curve of the horizon, one truth becomes undeniable. They cannot see their homes, not their house, not their street, not even a single building. From just 250 miles above Earth, every structure humans have ever built vanishes. The human eye simply cannot resolve such tiny details from that distance. That realization exposes something profound about perspective. Distance obliterates detail. From the vantage point of the International Space Station, entire neighborhoods blur into indistinct smudges. Cities dissolve into faint clusters, borders fade, and entire countries merge into an intricate patchwork of greens, browns, and blue. What once seemed unimaginably large now becomes impossibly small. Now imagine stepping even further back. At 1,000 miles up, states dissolve into faint silhouettes. At 10,000 miles, continents blur together until Earth transforms into a glowing blue sphere suspended in blackness. The world that once seemed infinite when you stood in your backyard suddenly fits neatly within your gaze. But this optical illusion cuts both ways. From our perch on Earth, we see ourselves as substantial, yet zoomed out, we shrink to insignificant. Meanwhile, the void that envelops us expands beyond all comprehension. The darkness, stretching outward from our fragile world, goes on for distances so vast that comparing them to the size of Earth feels almost meaningless, as though we were trying to measure an ocean with a grain of sand. Here's a thought experiment. Imagine Earth shrunk down to the size of a marble on your desk. Now, keeping that scale, place the nearest star, Proxima Centauri, over 4,000 miles away. That marble would sit utterly alone in an expanse of emptiness, stretching farther than the distance from New York to Los Angeles. That's how empty the cosmos truly is. This enormous gulf of nothingness defines our place in the universe. We inhabit a tiny speck, adrift in a vacuum, so deep that even light, moving at an unimaginable 170 million miles per hour, needs years to travel from one star to the next. Yet, despite that desolation, we are not alone. We're passengers on something grander, a sprawling congregation of stars, planets, and nebulae that together form our home galaxy. But even understanding our galactic neighborhood brings its own peculiar challenge. Just as astronauts can't spot their own homes from orbit, we can't truly see the galaxy we live in. Not directly. The light illuminating your surroundings right now began a journey so long ago that every human achievement pales beside it. Take the light from our nearest stellar neighbor, Proxima Centauri. It began its voyage over 4 years ago. That means the photons reaching your eyes at this very moment left that star when the world was different, when other songs filled the air, when people held different jobs, when global events had not yet unfolded. To give that distance meaning, consider this. When Christopher Columbus sailed across roughly 4,000 miles of ocean from Spain to the Americas, it was regarded as the edge of human daring, the ultimate test of courage and imagination. Sailors feared monsters and endless storms. They believed the horizon could swallow them whole. That was 4,000 miles. Now imagine 25 trillion miles. That's how far Proxima Centauri is from Earth. 25 trillion miles of empty space. If you somehow drove a car non-stop, no brakes, no sleep, full speed day and night, it would take you over 40 million years to cross that distance. 40 million years of relentless motion just to reach the closest star. This is the true scale of our galactic landscape. Those tiny twinkles scattered across the night sky, they aren't faint because they're small, but because they're unimaginably far. Each one is a roaring sphere of nuclear fire, often far larger and brighter than our sun. But space stretches so drastically between them that even light takes years to bridge the gaps. Our galaxy, the Milky Way, houses around 400 billion of these distant suns. Some are mere light years away, like Proxima Centauri. Others shine from distances of 50,000 light years or more. Each one hurls photons outward across the void, their light racing toward us from every direction. Some of that light began its journey before humanity existed, before life had even crawled onto land. Other rays set off billions of years ago, carrying ancient messages from an era when the Earth itself was still forming. When you look up at the stars, you're not just seeing the night sky, you're witnessing time itself. Each point of light is a postcard from the past. Some of those stars may no longer exist, their final bursts of energy still traveling toward us, ghostly remnants of cosmic history. And that's the strange paradox of existence. We live inside something so enormous that we can never see it whole. Like ants on the face of a clock, we explore small parts of a grand design, but will never step back far enough to grasp the entire mechanism. The light from the farthest edge of our galaxy has been en route for over 100,000 years, a century of millennia, carrying whispers from regions so remote they might as well belong to another universe entirely. Now imagine holding a single grain of sand between your fingers. Feel its minuscule weight, see how it barely presses against your skin, how easily it could be lost with a breath. That tiny particle, just 1 millimeter across, is among the smallest objects you can still manipulate with your bare hands. Now, for perspective, let that grain represent Earth. Every ocean, mountain, and city, every human life that ever existed, shrunk down to this tiny speck. The totality of human history compressed into something you could accidentally inhale. On this scale, your neighborhood doesn't even exist. Your city, no matter how sprawling, becomes a microscopic imperfection on that grain's surface. Even metropolises, like Tokyo or New York, shrink beyond visibility, requiring a microscope just to detect. And yet, we've only begun scaling down. If Earth were this single grain of sand, our moon would be a small pebble floating roughly 20 feet away, silent, distant, and forever circling that tiny dot of life adrift in the void. Imagine our sun, transformed into a bright beach ball, sitting half a mile down the road. Now picture Jupiter as a shimmering marble, rolling roughly 3 miles away. These distances already push the limits of what feels tangible to us. Half a mile seems walkable. 3 miles feels like a stretch, a decent trek on foot. But now, on this same scale, our nearest neighboring star, Proxima Centauri, would sit a staggering 125,000 miles away. You couldn't drive there. You couldn't hop on a plane. You would need a rocket powerful enough to cross that immense void, even in this miniature sand grain-sized universe. This scale model unveils something startling about our cosmic neighborhood. The distances between the planets in our solar system, which already seem mind-boggling, are minuscule compared to the yawning emptiness separating one star system from another. We exist within a compact bubble of warmth and matter, cocooned inside an overwhelming sea of nothingness. On this scale, our entire solar system would fit neatly inside a circle only about 10 meters wide, but the next closest solar system would be over 125,000 miles away. That's 12,000 times farther than the entire width of our own solar family. And yet, even these massive numbers barely scratch the surface of the scale of our galaxy. If we kept shrinking everything to the same proportions, our Milky Way would stretch an incredible 11 billion miles from edge to edge. 11 billion miles, a number so large that even light speeding along at 670 million miles per hour would need 16 hours just to cross from one side to the other. But even this example fails to truly convey the weirdness of galactic scale. So far, we've only been talking about distance. Now let's talk about motion. Right now, as you read these words, you are hurtling through space faster than any human-made vehicle has ever traveled. You're not only spinning with Earth's rotation, which propels you eastward at about 1,000 miles per hour, and not just orbiting the sun at 6,000–7,000 miles per hour. You're part of something even grander. Our entire solar system is hurtling through the Milky Way at an astonishing 560,000 miles per hour. That's 500,000 miles every single hour. To put that in perspective, the fastest fighter jets top out around 50. The legendary Concorde, once the symbol of supersonic flight, managed roughly 1,000. Even rockets escaping Earth's gravity only hit about 25,000 miles. Yet, as you sit still in your chair, you are silently racing through the galaxy at speeds that make all human travel seem like slow motion. But what is pulling us forward so quickly? The answer is gravity, not from our sun, but from the immense mass concentrated at the heart of our galaxy. The sun, along with its family of planets, moons and asteroids, orbits this central point, a gravitational anchor located around 26,000 light-years away. Picture our solar system as a bead on an invisible string, whipping around that distant core in a cosmic dance. The scale of that string is incomprehensible. Light itself needs 26,000 years just to cross it. This orbit carries our entire solar system on a path so vast that completing just one revolution around the galactic center takes 20. The last time we were in this same position, Earth looked nothing like it does today. The supercontinent Pangaea had barely formed, dinosaurs hadn't yet appeared. The oceans were filled with simple life forms, primitive creatures drifting through shallow sea. In all of Earth's 4.5 billion year history, our planet has completed fewer than 20 full orbits around the galaxy. That means Earth is roughly 18 galactic years old. Let that sink in. Everything we know about human civilization, from the first shipped stone tools to the International Space Station, has unfolded in less than 1% of a single galactic orb. Entire empires have risen and crumbled, species have evolved and vanished, all while we've moved through a mere sliver of our cosmic neighborhood. This perspective raises an obvious question. What exactly sits at the heart of this slow, powerful rotation? What kind of object could exert such an immense gravitational force that it can hold hundreds of billions of stars, including ours, in its grip? For most of human history, we imagined ourselves at the center of everything. Ancient astronomers pictured Earth as the unmoving center of creation, with the sun, moon and stars circling around it in perfect harmony. It felt right. After all, we feel no motion beneath our feet, and the sky above us moves like clockwork. To our ancestors, the idea that we were the stationary center of the universe seemed not just reasonable, but obvious. That belief persisted for centuries, until we started looking close. With better telescopes and careful measurements, astronomers realized the uncomfortable truth. Earth isn't the center of anything. Our planet revolves around the sun. That revelation stung, but perhaps, we thought, the sun still sat at the center of the universe, a modest consolation. Then in 1917, astronomer Harlow Shapley shattered even that illusion, studying globular clusters, dense spheres of ancient stars that orbit our galaxy like fireflies circling a bonfire. He began measuring their distances and mapping their position. What he discovered changed astronomy forever. These clusters didn't gather around the sun. They didn't even cluster around our local region of space. Instead, they revolved around a point, some 30,000 light-years away, in the direction of the constellation Sagittarius. That finding was shocking. It meant our solar system wasn't near the center of the galaxy at all. We weren't even close. We lived far out in the galactic suburbs, a quiet, unremarkable corner of the Milky Way. Shapley had revealed that our galaxy stretched nearly 100,000 light-years across, with our solar system sitting roughly 26,000 light-years from its core, much closer to the outer edge than to the middle. If the galaxy were a pizza, we'd be somewhere near the crust, not basking near the rich, flavorful center. Ironically, that cosmic suburban location is what makes our existence possible. The galactic center is a violent, radioactive storm, a chaotic zone of intense gravity and deadly radiation that would render nearby planets lifeless. Our distant position offers stability, a calm refuge, where complex life has the time to evolve and thrive over billions of years. Still, Shapley's discovery sparked another question. What could possibly sit 30,000 light-years away, that's massive enough to keep hundreds of billions of stars locked in orbit? What kind of entity could generate that much gravity? The answer would take decades to uncover, and when scientists finally did, the truth was far stranger than anyone had dared imagine. But before they could find it, astronomers faced a maddening problem. one that still challenges us today. How do you measure something you can't step outside of? How do you map a forest when you're trapped beneath its trees? How do you determine the size of a city when you can never leave its limit? That was the puzzle astronomers faced as they tried to understand the true scale of our galaxy, a cosmic mystery hidden in plain sight. Harlow Shapley tackled one of astronomy's greatest mysteries using a brilliantly indirect approach. Since he couldn't physically step outside the Milky Way to measure it from the outside, he did the next best thing. He charted the positions of globular clusters, those dense, ancient spheres of stars that orbit the galactic center like a scattered halo of cosmic lanterns. Shapley understood that these clusters weren't randomly placed. They formed a kind of spherical shell around our galaxy. If he could determine how far away enough of them were, he could effectively sketch the boundaries of the Milky Way in 3 dimensions. The clusters would act as reference points, marking the unseen edges of our vast stellar city. But there was a catch. How could anyone possibly measure distances to objects tens of thousands of light years away? For that, Shapley turned to an ingenious natural tool: Cepheid variable stars. These remarkable stars rhythmically pulse brighter and dimmer over time, and the speed of that pulsing reveals something profound: their true brightness. A Cepheid that pulsates slowly is inherently brighter than one that flickers quickly. This relationship gave Shapley what astronomers now call a cosmic yardstick. By measuring a Cepheid's pulse rate, he could determine its actual luminosity. Then, by comparing how bright it appeared from Earth, he could calculate its distance, because light from farther objects appears dimmer. Using this method, Shapley measured the distances to dozens of globular clusters scattered across the heaven. When he plotted their positions, a grand pattern appeared. The clusters formed a vast sphere roughly 100,000 light-years across, far larger than anyone had imagined. Even more astonishing, our solar system wasn't at the center of it at all. It sat roughly 2/3 of the way toward the edge. This revelation shook the scientific world. Before Shapley's work, astronomers believed the Milky Way was just a few thousand light-years wide, a relatively small neighborhood of stars. But Shapley's map revealed that our galaxy was a true giant of the cosmos. To cross its full diameter, a beam of light traveling at 670 million miles per hour would take 100,000 years. Amazingly, his early 20th century measurements have stood the test of time. Modern instruments have refined the numbers slightly, but Shapley's scale was astonishingly accurate given the primitive tools of his era. Yet even Shapley's vision only captured the visible part of our galaxy, the portion made of stars, gas, and dust. What he couldn't see was that the Milky Way is wrapped in something vast and invisible: dark matter. This mysterious substance can't be seen, touched, or detected by ordinary instruments. But its presence outweighs everything visible by about 20 to 1. In fact, all the stars, planets, nebulae, and interstellar dust combined make up just 5% of our galaxy's total mass. The other 95% is dark matter, unseen, untouchable, yet absolutely essential. How can we be certain it exists if we can't observe it directly? The same way we know the wind exists, by watching its effects. Stars in the galaxy's outer regions orbit far too quickly to be held in place by the gravity of visible matter alone. If only the stars and gas were providing gravitational pull, these fast-moving stars would simply fly off into space. Something massive and unseen must be keeping them bound, an invisible gravitational halo surrounding the Milky Way. This dark matter halo is enormous, stretching nearly 2 million light-years from edge to edge, roughly 20 times the diameter of the visible galaxy. Imagine our glowing spiral of stars as a narrow beam of light in a dark room. The dark matter halo would be the entire room itself, silent and unseen, enclosing that tiny cone of brilliance. Within this invisible sphere, trillions upon trillions of dark matter particles drift through everything, including you, every second, completely undetectable. They don't emit light, don't reflect it, and don't interact with normal matter in any familiar way. They pass right through planets, stars, and people as though nothing were there. Astronomers estimate that the Milky Way's halo holds between 600 billion and 3 trillion solar masses worth of dark matter. This unseen mass shapes not only our galaxy's structure, but also its entire evolution, influencing the birth of stars, the motion of clusters, and even the fate of cosmic systems. The reality is staggering. Most of the universe is made of something we cannot see or even fully comprehend. Everything we know, stars, planets, galaxies, and life itself, makes up only a tiny fraction of existence. And yet, even the mysterious dark matter halo has limits. Beyond that invisible boundary lies something even more extraordinary, a frontier humanity has only begun to approach. In 1977, two robotic spacecraft, Voyager 1 and Voyager 2, were launched toward the outer planet. These twin explorers became the fastest human-made objects ever created, streaking away from Earth at nearly 38,000 miles per hour, fast enough to cross the entire United States in less than 5 minutes. Each carried golden records containing messages from Earth, greetings, music, and sounds of our world, in case they were ever found by intelligent beings among the stars. They also sent back breathtaking images of Jupiter, Saturn, Uranus, and Neptune, the outer worlds of our solar system seen up close for the first time. But as fast as they are, their speed is utterly insignificant on the galactic scale. Even at 38,000 bisama, Voyager 1 would need around 130,000 years just to reach the nearest star, if it were even pointed in that direction. To put that in perspective, that's 10 times longer than all of recorded human civilization, and that's only the beginning. To cross the entire Milky Way from end to end at that same speed would take an unimaginable 1.7 billion years of non-stop travel. That's longer than the entire history of complex life on Earth. When Voyager began its journey, if you rewound time by 1.7 billion years, Earth was home only to simple microbes. No animals, no plants, no oxygen-rich atmosphere. Life as we know it didn't yet exist. During the time it would take Voyager to cross our galaxy, single-celled organisms would evolve into humans, rise into civilizations, and possibly disappear again, all while the tiny spacecraft continued its lonely voyage through the dark. This perspective puts the unimaginable distances between stars into a profoundly biological context. The entire evolutionary journey, from simple microbes to mammals and minds capable of self-reflection, has unfolded in less time than it would take to merely cross our galactic neighborhood. Even at the fastest speed humanity has ever achieved. And that's assuming the Voyager probes could somehow maintain their velocity forever, never losing power, never breaking apart, never colliding with a speck of cosmic dust along the way. In reality, both Voyager 1 and Voyager 2 will fall silent within the next decade as their nuclear power sources slowly decay. Once their instruments shut down, they'll continue gliding endlessly through the darkness, cold, silent relics of human curiosity, drifting between the stars as lifeless metal husks, never able to send home another whisper about what lies ahead. The space between star systems is almost beyond comprehension. It's not just empty, it's a near-perfect vacuum. Voyager currently moves through regions where there's less than 1 atom per cubic centimeter. That's emptier than any vacuum humans can create in a laboratory. The odds of either spacecraft encountering another solid object in the next several million years are virtually zero. This vast emptiness defines the structure of our galaxy. While stars gather together in a relatively thin disk, the space separating those points of light is enormous, oceans of nothingness, between isolated islands of brilliance. Yet despite all that emptiness, the Milky Way teems with stars. Our galaxy contains more stars than there are grains of sand on every beach of Earth. Combined, an estimated 400 billion of them. Try to imagine counting them one by one. Even if you named one star every second, 24 hours a day, it would take you more than 12,000 years to finish. If each of the 8 billion people alive today took responsibility for counting an equal share, every person would still need to count roughly 50 stars to complete the tally. And those stars, they come in endless varieties. Blue-white giants that burn their fuel in just a few million years, glowing with fierce intensity, and tiny red dwarfs that sip their fuel so slowly, they'll continue shining for hundreds of billions of years, long after our sun fades away. Some stars are barely massive enough to sustain nuclear fusion. Others pack dozens of solar masses into incredibly dense, blindingly hot cores. The diversity extends beyond mere size and color. Many stars come in pairs, orbiting one another in graceful gravitational dancing. Others live in crowded clusters, where hundreds of suns share tight, chaotic neighborhoods. In these stellar cities, gravity and radiation interact in wild, unpredictable ways, creating exotic phenomena that astronomers are still trying to fully understand. Some stars pulse rhythmically, acting like cosmic lighthouses, sweeping their beams through the dark. Among these hundreds of billions of stars, astronomers estimate there are at least 100 billion planets orbiting in the so-called habitable zones, regions where liquid water could exist on the surface. That means 100 billion potentially life-supporting worlds, scattered across the spiral arms of our galactic home. It's impossible not to wonder how many of them might harbor life. How many could cradle oceans, forests, or civilizations advanced enough to look up at their night skies and ask the same questions we do right now? The oldest stars in the Milky Way formed more than 13 billion years ago, when the universe itself was still in its infancy. These ancient suns have seen everything, from the era when heavy elements barely existed, to today's universe rich with complex chemistry and rocky planets. Some of those old planetary systems could have sustained life for billions of years longer than Earth has existed. But this immense population of stars isn't spread out randomly. The Milky Way's stars are organized into a flattened disk, about 1,000 light-years thick, and roughly 100,000 light-years wide. Our solar system lies buried within this disk, around 26,000 light-years from the galactic center. From here on Earth, when we gaze toward the center of the galaxy, we see the densely packed light of countless distant stars, merging into a milky glow that stretches across the night sky, the namesake of our galaxy itself. What looks like a faint hazy band is actually the combined light of billions of suns, too far away for the human eye to distinguish individually. Yet these 400 billion visible stars are just the beginning. Chapter 10. The Galactic Clockwork. How long it takes the Milky Way to spin once. Our galaxy rotates like a colossal cosmic pinwheel, but it doesn't turn like anything we experience on Earth. When a record spins on a turntable, every point from the center to the edge completes one full revolution in the same amount of time. But the Milky Way plays by a different set of rules. Stars near the galactic core orbit much faster than those farther out, much like runners on an oval track where the inner lanes move quicker than the outer one. Our own solar system, located about 26,000 light-years from the center, completes a full galactic orbit roughly every 20-50 million years. Astronomers call this a cosmic year, and it's a powerful way to grasp the scale of galactic time. Since Earth formed 4.5 billion years ago, our planet has completed only 18 galactic orbits, just 18 trips around the Milky Way. Everything that's ever happened on Earth, from its molten beginnings to the rise of human civilization, has unfolded in less than 20 cosmic years. Think about that. When Earth last occupied the same position it does now in its orbit around the galaxy, it was 250 million years ago, during the late Paleozoic era. The supercontinent Pangaea had only just begun to split apart. Dinosaurs didn't exist yet. The most advanced life forms were primitive reptiles and amphibians. No mammals, no flowers, no grass. The entire reign of the dinosaurs, from their emergence to their extinction 65 million years ago, lasted only about 1/4 of a single galactic year. And the entirety of human civilization, from the first cities to today's technology, accounts for less than 1/10,000th of that same span. If we compressed the galaxy's rotation into a single Earth year, all of human history would take place in the final seconds before midnight on December 3rd. This slow, graceful rotation has fascinating consequences for our stellar neighborhood. Stars that currently appear close together will slowly drift apart over millions of years. The constellations we know today, Orion, Ursa Major, Cassiopeia, will eventually dissolve into unrecognizable patterns. Meanwhile, our sun follows a gentle up and down motion as it orbits the galactic center. Every 33 million years, it rises above the plane of the galactic disk, before drifting back down below it, completing one full vertical oscillation, roughly every 60. Some scientists speculate that this rhythmic motion might even be linked to mass extinction events on Earth. When our solar system passes through the dense central plane of the galaxy, it encounters greater concentrations of gas, dust, and debris, conditions that could gravitationally disturb the distant Oort cloud, sending comets hurtling toward the inner planet. This complex web of motions, stars orbiting at different speeds, weaving and drifting through the galactic disk, is known as differential rotation, and at the very heart of it all lies something so massive and dense that it bends space and time itself. Sagittarius, AOS, the supermassive black hole at the very heart of our galaxy, contains the staggering mass of nearly 4 million suns. Yet all of it is squeezed into a region smaller than our entire solar system. 4 million suns compressed into a single, compact point of unimaginable density. This gravitational giant acts as the cosmic glue that binds our Milky Way together, its immense pull holding nearly 400 billion stars in orbit, weaving them into one vast spiraling structure. A black hole of this scale defies every rule of ordinary experience. Near its event horizon, the invisible boundary where gravity becomes so strong that not even light can escape, space itself bends and contorts into impossible geometries. Time slows down the closer one drifts toward that edge. A clock near Sagittarius AOS would tick far more slowly than one in your living room on Earth. We can't observe this black hole directly. It traps all light and matter that stray too near, but its presence reveals itself through its influence on the stars and gas swirling around it. Some of those nearby stars race through space at blistering speeds exceeding 3,000 kilometers per second, whipping around an unseen anchor with orbital periods that last just years, short by galactic standards. Occasionally, this gravitational monster, when a gas cloud or an unlucky star drifts too close, its material gets pulled inward, spiraling through the accretion zone at tremendous speed. Friction superheats the infalling gas to millions of degrees, causing it to flare brightly in X-rays and radio waves before vanishing beyond the event horizon, gone forever. Recent studies show that Sagittarius AOS spins at nearly the theoretical maximum speed for any black hole. It rotates so rapidly that it literally drags space-time along with it, a bizarre effect known as frame dragging, one of Einstein's most astonishing predictions from his general theory of relativity. Astronomers believe this colossal object began forming early in the Milky Way's history. It likely started as a much smaller black hole and grew by devouring gas, dust, and stars over billions of years. As its mass increased, its gravitational reach expanded, shaping the swirling disk of matter that became our galaxy. The environment near the galactic core is nothing short of violent. Intense radiation, chaotic magnetic fields, and immense gravitational forces make it one of the harshest regions in existence. Massive stars there live short, brilliant lives before exploding as supernovas, pouring even more energy into an already turbulent zone. Despite being about 26,000 light-years away from this chaos, our solar system still feels its gravitational pull. Sagittarius AOS acts as the central anchor point, keeping every star, including our own sun, bound in orbit within this vast celestial dance. But this black hole is just one piece of a far greater puzzle, the structure of the Milky Way itself. And in trying to understand that structure, astronomers face a challenge unlike any other civilization in the cosmos. We live inside the very thing we're trying to study. Every other galaxy can be admired from a safe distance, photographed in its entirety, mapped from the outside. We, however, are stuck within the confines of our own galactic disk, forced to piece together clues like detectives trapped inside the crime scene. It's like trying to map an entire city while locked in a windowless basement. You can send out scouts to report from nearby streets, but you'll never step back to see the city's full design. That's our situation exactly. When we gaze toward the Milky Way's center, we look through a flat, crowded disk filled with stars and dust. Dense clouds of interstellar matter block our view, like thick fog swallowing distant light. Visible light from the galactic core can't reach us. It's absorbed or scattered before it gets close. Beyond a few thousand light-years, everything fades into darkness. Thankfully, not all wavelengths are blocked. Radio and infrared light can slip through the murky dust, allowing us to peer deeper into the galactic interior. But even with these longer wavelengths, our view remains partial, a patchwork of fragments rather than a full portrait. Astronomers observing distant galaxies have the luxury of perspective. We do not. Looking along the galactic plane adds another problem. Billions of stars overlap in our line of sight, blending into a glowing ribbon, the Milky Way band that stretches across our night sky. At those distances, individual stars blur together, and we lose all depth perception. Yet, being inside our galaxy also offers a unique advantage. We can examine individual stars, gas clouds, and planets far more closely than any observer outside could hoped. We can measure their movements, map chemical compositions, and track planetary systems with extraordinary precision. Modern missions like Gaia have revolutionized this effort. The Gaia spacecraft has mapped the exact positions and motions of over 1 billion stars, creating the most accurate 3D map of our galactic neighborhood ever assembled. These data have revealed patterns in stellar motion that help us decode the Milky Way's shape, rotation, and history. But we'll never step outside our galaxy for a full snapshot. We are bound to remain inside it like explorers forever confined to the rooms of a colossal mansion, able to explore its corridors, but never glimpse the entire exterior. Even so, this limitation hasn't stopped us from uncovering wonders. One of the most surprising is the realization that the Milky Way's graceful spiral arms, the luminous swirls defining its shape, are not fixed, solid structures at all. They're more like cosmic traffic jams than rigid arms of matter. Most people picture spiral arms as permanent features, rotating through space like the blades of a pinwheel, but that's an illusion. The stars and gas making up those arms are constantly in motion, entering and leaving the crowded zones. The arms themselves are patterns, waves of density that travel through the galactic disk. Imagine looking down on a busy highway from above. Cars slow down and cluster near construction zones, forming dense traffic jams that appear to crawl along the road. The jam seems solid, but the cars inside it are constantly changing. That's precisely how our galaxy's spiral arms behave. Stars orbit the galactic center at varying speeds, passing in and out of these compression zones. The arms, meanwhile, persist as moving patterns, waves that trigger bursts of star formation as they squeeze gas clouds to higher density. Young, bright blue stars ignite in these regions, lighting up the spiral arms from within. The massive stars burn out quickly, exploding as supernovas before they can drift far, which makes the arms appear filled with youthful luminous clusters. Our solar system currently lies between two of these major arms, in a smaller spur known as the Orion Arm. We last crossed a main spiral arm around 50 million years ago, and won't encounter another for roughly 10 million years. These crossings can subtly affect Earth's environment, as denser regions bring more gas, dust, and radiation, possibly influencing climate and even evolution. Interestingly, the spiral arms themselves rotate far slower than individual stars. This differential motion allows stars to drift in and out of the arms over time, preventing the Milky Way from winding itself into oblivion. Scientists still debate what sustains these spiral waves. Some theories suggest gravitational interactions with smaller neighboring galaxies inject energy into the system. Others point to the Milky Way's central bar structure as a driver of these patterns through complex gravitational dynamics. Modern observations reveal that our galaxy's spiral structure is far from simple. It's riddled with spurs, branches, and gaps that shift over tens of millions of years. And beyond even these iconic arms lies something grander still. Our Milky Way is not alone. It travels through the void accompanied by smaller galaxies bound to it by gravity. When we zoom out far enough, a stunning picture emerges. A family of satellite galaxies orbiting our own like glowing fireflies, circling a lantern. The most famous of these companions, visible from the southern hemisphere, are the large and small Magellanic Clouds. These faint, misty patches of light puzzled ancient sailors who used them for navigation, unaware they were entire galaxies. The Large Magellanic Cloud contains around 10 billion stars and lies about 160,000 light-years away, The Small Magellanic Cloud holds about 3 billion stars at a distance of roughly 2. Both lie beyond the visible edge of our galactic disk, but remain embedded within our extended dark matter halo. Yet their orbits are far from peaceful. The Milky Way's immense gravity distorts them, stretching their stars into elongated strips. Tidal forces rip gas and stars from their bodies, leaving behind vast ribbons of debris, celestial scars of their ongoing struggle. And these are just the largest companions. More than 30 smaller satellite galaxies orbit our own, bearing names like Draco, Sculptor, and Forn. Many are so faint that we've only recently detected them with modern instruments. Some are ghostly collections of dark matter, with only a sprinkling of visible stars, nearly invisible despite their massive weight. Over time, our galaxy's gravity slowly consumes these smaller neighbors, a cosmic act of cannibalism that fuels its growth. This process hints at a deeper truth. What we see in the night sky, the glowing disk of stars, is only the bright heart of something far larger and largely invisible. Recent measurements suggest our dark matter halo stretches nearly 2 million light-years from the galactic center, about 20 times farther than the visible disk. Think of our galaxy as a cherry pit sitting in the center of a basket. The cherry represents all the stars, gas and dust we can see. The basketball, that's the immense sphere of dark matter, enveloping everything. This invisible halo outweighs our visible galaxy by at least a factor of 10, holding between 600 billion and 3 trillion solar masses worth of material. We exist deep inside this unseen ocean, like creatures unaware of the vast depths that surround them. The dark matter halo dictates the motion of everything inside it. Satellite galaxies orbit within this invisible sea, guided by forces they can never see. Their paths trace the true shape of our galaxy's gravitational skeleton. Simulations suggest that within this massive halo are thousands of smaller clumps, subhalos, moving like schools of fish through an invisible current. Some are dense enough to capture regular matter and form small galaxies. Others remain eternally dark. This halo also governs our galaxy's long-term evolution. Its gravity attracts intergalactic gas, feeding the Milky Way with fresh material for star formation. It even acts as a shield, deflecting high-energy cosmic debris that could otherwise disturb our galactic structure. Yet the edge of this halo fades gradually, blending imperceptibly into the greater web of dark matter that fills the universe. Even with its invisible cloak, the Milky Way itself is far from stable. It doesn't spin like a perfect disk. It wobbles. The galaxy flexes and warps like a spinning coin losing speed. The outer regions of our galactic disk ripple up and down, sending waves of motion toward the center. Recent data from variable stars show that this galactic warp slowly rotates backward, about 1/20th of a degree every million years, relative to the star's orbit. What causes this vast wobble? The culprit appears to be, once again, the dark matter halo. It isn't perfectly spherical, it's slightly flattened, more like an oblong football. This asymmetry exerts subtle gravitational torques on the stellar disk, making it wobble over time. Picture a spinning coin, gradually slowing as it loses momentum. It begins to tilt and shimmy before falling flat. Our galaxy behaves much the same way, except the friction comes from the misalignment between the rotating disk and the halo's shape. This wobble ripples through the Milky Way, influencing stars, gas clouds, and even our solar system. It compresses and stretches space locally, affecting the motion of objects thousands of light-years apart. By studying these warps and oscillations, astronomers can infer the invisible distribution of dark matter around us, the unseen architecture that defines the Milky Way's true shape and destiny. This gives astronomers one of the rare, direct opportunities to investigate the nature of dark matter on galactic scales. Yet, the behavior of our galaxy isn't shaped solely by invisible forces. Our neighboring satellite galaxies play an equally critical role in this cosmic dance. The large and small Magellanic Clouds, along with several smaller companions, each exert their own gravitational tug on the Milky Way's disk. Their orbital movements create additional torques, subtly altering the precession rate and the very pattern of our galaxy's warp. These discoveries reveal that the Milky Way is not a static structure, but a living, dynamic entity in constant flux, shaped by the gravitational interplay of both visible and unseen mass. However, the gentle wobbling of our galactic disk is just a prelude to a far more dramatic future. Roughly 4.5 billion years from now, our night sky will host one of the most breathtaking and inevitable cosmic events ever witnessed: the collision with the Andromeda Galaxy. Our nearest galactic neighbor, Andromeda, is careening toward us at an astonishing speed of about 250,000 miles per hour. This titanic system of over 1 trillion stars is on a direct collision course with the Milky Way in what astronomers call the most predictable catastrophe in cosmic history. When the two galaxies meet, they will merge into a new colossal structure, erasing the familiar shapes of both in the process. At present, Andromeda appears as a faint smudge of light in the autumn sky, barely perceptible to the naked eye. Yet, that soft glow contains more stars than our entire galaxy combined. Situated just 2.5 million light-years away, it's practically next door on the cosmic scale. As it draws nearer, Andromeda's gravitational force will begin distorting the Milky Way long before the actual impact. Our spiral arms will start to twist and stretch, streams of stars will be pulled outward, and vast bridges of interstellar matter will form between the two galactic giants. The eventual collision will not be an explosive impact, but rather a slow-motion ballet that unfolds over billions of years, so gradual that no single civilization could witness it from start to finish. Despite the vast numbers of stars involved, more than 1 trillion combined, direct stellar collisions will be exceedingly rare due to the immense distances separating each star. Instead, the galaxies will glide through each other like immense clouds of glowing fireflies, their gravitational forces scattering and reshuffling the orbits of countless suns. Our own solar system is expected to survive this encounter, though its ultimate fate remains uncertain. Simulations suggest that the sun might be flung toward the distant outskirts of the merged galaxy, or even ejected entirely into the cold emptiness of intergalactic space. In such a case, Earth could wander endlessly between galaxies, orbiting a lone star with no galactic home to call its own. Meanwhile, at the centers of both galaxies, two supermassive black holes, each millions of times heavier than the sun, will spiral inward and eventually collide. Their union will release more energy through gravitational waves than the sun will emit in light over its entire 10 billion year lifetime. The newly formed galaxy, dubbed Milky Way by astronomers, will look nothing like the graceful spirals we see today. Instead, it will resemble a vast elliptical galaxy, smooth and structureless, shaped like a cosmic football. But this cataclysmic event is not unique. It's a glimpse into the constant, violent evolution of the universe. Even now, the Milky Way and Andromeda are not drifting aimlessly. Both, along with hundreds of neighboring galaxies, are hurtling through space toward an immense and mysterious region known as the Great Attractor. Traveling at around 600 miles per second, our entire local group of galaxies is being pulled toward this enigmatic gravitational anomaly, located roughly 150 million light-years away, in the direction of Hydra and Centaurus. The Great Attractor lies concealed behind our galaxy's dusty plain, an area astronomers call the Zone of Avoidance, where thick clouds of gas and stars block our view. Yet, telescopes that observe in infrared and radio wavelengths have managed to peer through the veil, revealing colossal galaxy clusters: the Norma cluster, the Centaurus cluster, and the Hydra cluster, all contributing to the gravitational pull in that direction. But even these visible structures fail to explain the full magnitude of the attraction. There must be additional, unseen mass, perhaps immense concentrations of dark matter or entire hidden clusters, lurking beyond our sun. The true composition and extent of the Great Attractor remain one of astronomy's greatest mysteries. What we do know is that our galaxy doesn't drift randomly through the cosmos. It moves along gravitational currents set by the largest structures in the universe. We are passengers on a vast cosmic river, carried along by forces operating across incomprehensible distances. Beyond the Great Attractor lies something even larger, the shapely supercluster, an enormous collection of thousands of galaxies that may represent the final destination of our cosmic voyage. But closer to home, another type of galactic drama is constantly unfolding: our Milky Way's quiet predation on smaller neighbors. The Sagittarius dwarf elliptical galaxy is one such victim. This small system of around 4 billion stars is currently being torn apart by our galaxy's gravity as it attempts to orbit the Milky Way. Over billions of years, tidal forces have stripped away most of its stars, leaving long, elegant streams of stellar debris trailing across the sky. These streams, looping around our galaxy, mark the ghostly path of a galaxy being devoured alive. Each pass through the Milky Way's dense disk pulls more stars from the dwarf galaxy, reducing its mass until it finally dissolves completely. Simulations suggest that within a few billion years, the Sagittarius dwarf will vanish entirely, its stars fully absorbed into the Milky Way's structure. This process of galactic cannibalism is not unique. It's how large galaxies like ours grow. Many of the stars in our galactic halo once belonged to smaller galaxies that were captured and destroyed over the past 10 billion years. The Milky Way's smooth outer regions are, in truth, a graveyard of devoured galaxies. Even the large Magellanic Cloud, one of our brightest and most visible satellite galaxies, appears destined for the same fate. New measurements indicate it may not be in a stable orbit, but instead on its first inward spiral toward us. Over the coming billions of years, the Milky Way's gravity will peel away its outer layers of gas and stars, feeding new waves of star formation within our spiral arms as it dies. Smaller dwarf galaxies show similar signs of destruction. Their faint, stretched shapes testify to the tidal forces tearing them apart. These ultra-faint systems, often containing just a few thousand stars, are the latest prey in an ancient cycle of galactic feeding that has shaped the Milky Way's evolution. For billions of years, our galaxy has grown not by peacefully collecting gas from space, but by consuming other. The evidence is written all around us in the stellar streams, orbital debris, and the quiet remnants of galaxies long gone. For decades, astronomers debated whether our galaxy possessed another key feature seen in many spiral galaxies: a central body. Most spiral galaxies have a long, glowing structure of stars extending from the core, acting like the handle of a cosmic dumbbell. These bars help shape galactic evolution by channeling gas inward to fuel new stars, and influencing the formation of spiral arms. But identifying one in our own galaxy proved nearly impossible. Because we live inside the Milky Way, trying to map its structure is like trying to chart a forest while standing among the trees. Thick clouds of interstellar dust obscure our view of the galactic center, hiding its true shape. The mystery was solved in 2005, when NASA's Spitzer Space Telescope used infrared vision to peer through the dust. Unlike visible light, infrared radiation cuts through obscuring clouds, allowing astronomers to map the stars hidden in our galaxy's heart. What they found was astonishing: a vast stellar bar, stretching some 27,000 light-years across, rotating as a single, unified structure. This discovery explained numerous puzzling features of the Milky Way's dynamic. The bar's gravity helps sculpt the spiral arms, drives gas inward to feed our central black hole, and sparks new waves of star formation across the disk. Rotating faster than the sun's orbit, the bar completes a full turn every few 100 million years, creating periodic gravitational alignments that ripple through the galaxy. Over time, the bar slowly transfers its angular momentum outward, causing it to lengthen and grow more prominent. Simulations indicate that this structure likely formed within the past few billion years, a relatively recent addition in galactic history. Its discovery completely transformed our understanding of the Milky Way, revealing it to be not a simple spiral, but a barred spiral galaxy with a far more intricate internal design. Across the Milky Way, roughly 3 new stars are born each year, while 2 others reach the end of their life. This ongoing cycle of creation and destruction has shaped our galaxy for more than 10 billion years, forging the heavy elements that make planets and life itself possible. Every atom in your body, except hydrogen, was created in the heart of a star long before Earth even existed. Star birth isn't random, it occurs mainly in the spiral arms, where shockwaves compress vast clouds of gas. These regions, called stellar nurseries, glow brightly with the light of newborn stars. The most massive of these stars burn out quickly, living only a few million years before exploding as supernova. Each supernova releases more energy in moments than the sun will emit in its entire lifetime, sending shockwaves that trigger new rounds of star formation, a self-sustaining cycle of rebirth. Smaller stars like the sun, live far longer, providing steady energy for billions of years. When they die, they swell into red giants and then shrink to white dwarfs, tiny, dense remnants that can persist for eternity. Over cosmic time, each generation of stars has enriched the galaxy with heavier elements. The earliest stars formed from hydrogen and helium alone, but their deaths seeded space with carbon, oxygen, iron, and all the ingredients for planets and life. Our Sun, born 4.6 billion years ago, is at least a third-generation star, built from the ashes of countless earlier ones. Although star formation has slowed dramatically since its peak 10 billion years ago, it continues today, gradually transforming gas into stars and elements. Eventually, when the Milky Way's gas supply runs out, this great stellar cycle will fade to silence. Even the edges of our galaxy are not fixed. For years, astronomers thought the Milky Way's stellar disk ended around 50,000 light-years from its center. Beyond that, they expected only emptiness. But in 2018, data from the Gaia mission revealed stars orbiting far beyond, up to 100,000 light-years away, and beyond. Follow-up studies pushed that number to nearly 100, proving that our galaxy is far larger than anyone had imagined. The Milky Way's boundary, it seems, is still expanding, its story still being written in the stars. Recent measurements reveal that the Milky Way's dark matter halo stretches far beyond what we once believed, nearly 2 million light-years from its heart, extending around 20 times farther than the reach of our galaxy's visible stars. This means the true frontier of our galactic domain reaches almost halfway toward Andromeda, our closest large galactic neighbor. Such an immense extension challenges every established model of how galaxies form and evolve. How can our galaxy sustain coherent star populations at such extreme distances from its gravitational core? Stars orbiting at the edge of this enormous halo take over 1 billion years to complete just one revolution, meaning they've circled the galaxy only a few times since it first came into being. This discovery doesn't just stretch the boundaries of our galactic map, it reshapes our understanding of where the Milky Way ends and intergalactic space begins. If both our galaxy and Andromeda possess halos that each stretch about 2 million light-years, their outer boundaries may already overlap or touch. In a cosmic sense, the great collision between the Milky Way and Andromeda may have already started, just invisibly, through the mingling of their dark matter. The actual merging of their stellar populations, however, won't occur for another 4 billion years. Gravitational interactions with smaller companion galaxies may also explain the presence of distant stars far beyond the Milky Way's core. As our galaxy's powerful gravity tears apart these satellites, their stars are scattered across immense distances, forming stellar streams, delicate trails of light that weave through the outer regions of our galactic halo. Some of these streams could easily account for the stars now found drifting far beyond what was once thought the galaxy's outermost edge. The ever-expanding view of our galaxy's size is not mere speculation, it's the result of technological progress. Each generation of advanced telescopes and space missions pushes the limits of what we can see, revealing faint, hidden structures that redefine our place in the cosmos. It's likely that the Milky Way's true extent is even greater than we currently measure. Running through this colossal system are invisible magnetic highways, unseen filaments that direct the movement of charged particles across distances that make solar systems seem microscopic. These galactic magnetic fields, although thousands of times weaker than a household magnet, stretch across the full 100,000 light-year diameter of the Milky Way. They thread through interstellar space like cosmic electrical lines, shaping the flow of plasma and gas, and influencing the birth and death of stars across our galaxy. The field lines themselves twist in harmony with the Milky Way's spiral arms, wrapping around the galactic center in vast arcs that echo the structure of the star. This occurs because our galaxy's rotation twists and stretches the magnetic field, much like wringing a soap towel causes water to follow the twisted pattern of the fabric. These unseen magnetic pathways play profound roles in galactic dynamics that we seldom consider. Charged particles, such as cosmic rays accelerated by exploding stars, spiral along these magnetic routes, sometimes journeying thousands of light years before colliding with regions of denser material. These magnetic fields also shape star formation itself, providing a sort of pressure that can prevent gas clouds from collapsing too quickly. Depending on how the field lines bend or compress, they can either ignite or suppress new star formation in certain areas. This delicate magnetic balance helps explain why some regions of our galaxy burst with new stars, while others remain strangely quiet. Recent space missions have begun mapping this invisible architecture with unprecedented clarity. The European Space Agency's Planck mission, for instance, analyzed the polarized light emitted by interstellar dust grains, revealing how these tiny particles align themselves along local magnetic direction. The resulting maps show a complex web of magnetic filaments winding through the galactic disk like threads in a cosmic tapestry. These vast magnetic fields arise from the motion of electrically conducting gases, drifting through space. As clouds of ionized hydrogen move, they generate electric currents that in turn produce magnetic fields. The rotation of the galaxy amplifies and organizes these forces into the large-scale magnetic structure we observe today. The strength of these magnetic fields varies dramatically. Near the galactic core, where our supermassive black hole and clusters of high-energy stars reside, the magnetic field is hundreds of times stronger than the average across the galaxy. Out in the calmer regions between the spiral arms, however, the fields weaken so much that they barely affect the movement of charged particles. Occasionally, magnetic reconnection events occur, moments where field lines snap and realign, releasing titanic bursts of energy that can ripple across interstellar space. These magnetic phenomena not only shape the Milky Way's internal structure, but also link it to the wider electromagnetic web of the universe itself. When we step back to view the cosmic stage as a whole, our galaxy is but one modest participant in an unimaginably vast population. Astronomers now estimate that the observable universe contains around 2 trillion galaxies, each a sprawling city of stars, gas and dark matter. 2 trillion, that's far more than any previous count, revealing a cosmos overflowing with stellar metropolis. Our Milky Way, massive as it seems, is less than 1/trillionth of this population. With roughly 400 billion stars, our galaxy sits comfortably in the middle of the cosmic scale, neither small nor particularly large. Some galaxies contain just a few million stars, others boast over 1 trillion, dwarfing our home entirely. Structurally, the Milky Way is quite typical among spiral galaxies. About 60% of all known galaxies share this familiar architecture: central bulges, rotating disks, and luminous spiral arms. Yet despite its common form, the Milky Way possesses characteristics that make it unusually stable and quiet. Unlike galaxies in dense clusters, where collisions and gravitational chaos frequently distort their shapes, our galaxy occupies a peaceful region of space. It resides far from major galactic crowds, allowing its spiral pattern to endure relatively undisturbed for billions of years. Though it interacts with smaller satellites and is on a slow collision course with Andromeda, our location offers rare tranquility in an otherwise tumultuous universe. Chemically, our galaxy aligns with other spirals of similar mass and age. Its metal content, the abundance of elements heavier than hydrogen and helium, suggests a steady history of star formation and recycling. Our Sun, slightly richer in these heavy elements than average, is typical of stars born in galaxies like ours. Today, the Milky Way's star formation rate matches that of most spiral galaxies, in what astronomers call the Green Valley, a transitional stage where star birth gradually slows as available gas dwindles. In essence, our galaxy is gracefully aging, its stellar engine burning through its last major reserves. This cosmic context offers a humbling perspective. Despite containing hundreds of billions of stars, and stretching across 100,000 light-years, our galaxy remains just one among trillions, an ordinary spiral in an extraordinary universe. And yet this ordinariness raises profound questions about life beyond our own. If so many galaxies exist, how many worlds like ours might orbit distant suns? The Milky Way doesn't simply float in isolation, it moves along a filament of the universe's largest known structure, the cosmic web. This immense network of dark matter filaments links galaxy clusters across billions of light-years, creating a spiderweb-like architecture that serves as the universe's scaffolding. Our galaxy rides along one of these strands, following a gravitational path determined by dark matter concentrations formed shortly after the Big Bang. Imagine it like a train gliding along invisible tracks. The cosmic web's filaments guide the motion of galaxies, shaping their destiny. These filaments, which contain nearly 60% of all matter, connect vast nodes where thousands of galaxies congregate, separated by enormous empty voids that span hundreds of millions of light-years. Computer simulations suggest that this web emerged naturally from slight density ripples in the early universe. Over eons, gravity amplified these ripples, pulling matter into threads and clusters, the very structure we now see stretching across the heaven. Our local group, home to both the Milky Way and Andromeda, travels along one such filament, leading toward the Virgo cluster, a massive congregation of more than 1,300 galaxies about 54 million light-years away. Along this filament lies not just galaxies, but also enormous reservoirs of superheated intergalactic gas, a diffuse plasma glowing faintly in X-rays, serving as raw material for future galaxies yet to form. Modern observations have even begun to map the cosmic web directly, tracing the X-ray glow of this hot gas and detecting how its invisible dark matter bends the light from distant galaxies, a subtle effect called gravitational lensing. These measurements confirm that our Milky Way indeed glides along one of the universe's main arteries. The cosmic web doesn't just connect galaxies, it also regulates the gas flowing inward along these filaments fuels star formation, while energetic winds and radiation from galaxies flow back out along the same paths, an endless exchange between galactic and intergalactic realms. If we could somehow step outside the Milky Way and look back, the sight would be breathtaking. We'd see a graceful spiral of shimmering light, billions of stars arranged in sweeping arcs, glowing in hues of blue and gold. The spiral arms dotted with newborn stars would sparkle like strings of cosmic lanterns, while older yellow stars would fill the inner disk with a softer, steadier light. A bar-shaped core of ancient stars would stretch across the center, slowly rotating around the supermassive black hole that anchors our galaxy. Dark ribbons of dust would trace the spiral arms, cutting intricate shadows that mark regions where new stars are forming. Surrounding the disk would be a halo of ancient clusters, tiny points of light orbiting like fireflies around a vast celestial bonfire. If seen edge-on, our galaxy would appear astonishingly thin, a cosmic disk only a fraction of its diameter thick, subtly warped at the edges, like a vinyl record left in the sun. Tiny satellite galaxies would orbit nearby, and faint arcs of torn starlight would mark the scars of their disintegration under the Milky Way's pull. In the distance, Andromeda would glow faintly, its spiral arms stretching toward us across the void. But we will never truly see this view. We are trapped inside our own galaxy, like observers living their entire lives within a magnificent cathedral, able to admire individual details, but never to step outside and witness the full structure. This is the essence of the human cosmic condition. We dwell within something so vast that we can never perceive it in totality. Instead, we reconstruct our understanding piece by piece, through observation, simulation, and imagination. And despite these limits, humanity has managed to map and model the Milky Way with remarkable precision. Through centuries of effort, we've discovered that our home spans over 100,000 light-years, contains some 400 billion stars, and moves as part of an immense cosmic network. We are, in every sense, citizens of infinity, inhabitants of a galactic metropolis beyond comprehension, forever striving to grasp our place within the grand architecture of the universe.